Hello all. Welcome to another lecture of the regression analysis course. In this video, we are going to check if the estimator of beta obtained using ordinary least squares method is unbiased or not. And if it is unbiased, what is the variance of that estimate? Let's start. Given the multiple linear regression model, y is equals to x beta plus epsilon, by now we know what each of these symbols represents. Y is the response vector, x is the matrix of predictors, beta is the vector of unknown parameters that we want to estimate, and epsilon is the error term representing random variation not captured by the model. Now, if someone gives us a data set, we can observe x and y, but not beta. So the question is, how do we estimate this beta? In the last video, we saw that we can estimate beta by minimizing the sum of squared errors, and this method is known as the ordinary least squares estimation. And using matrix notation, the estimate we get is beta hat is equals to x transpose x whole inverse x transpose y. Now comes the important question. Is this estimate a good estimate of beta? So now we're going to prove that it is unbiased and also find the variance of this estimate beta hat. Let's start by finding the estimation error. Estimation error refers to the difference between the estimated value of a quantity and its true value. So if theta is the true value and theta hat is the estimate of theta, then the estimation error is just the difference between the prediction and the true value. Basically, it measures how far off your estimate is from the actual target. So if we try to find an estimation error of the coefficient estimator beta hat, it would be equals to beta hat minus beta. Now if we plug in the value of beta hat over here, because we have just estimated it using ordinary least square estimation method, it would be equals to x transpose x whole inverse x transpose y minus beta. We are dealing with multiple linear regression model. Therefore, this y we have is equals to x beta plus epsilon. We put that y is equals to x beta plus epsilon in the equation, and this is what we get. Next, we use the distributive property for multiplication and multiply x transpose x whole inverse x transpose with x beta and epsilon. When we do that, we get these three terms. X transpose x whole inverse x transpose x beta plus x transpose x whole inverse x transpose epsilon minus beta. And now let's try to simplify it. Let's start by looking at the first term, which is x transpose x whole inverse x transpose x beta. In this term, we group x transpose and x together. And when we do that, we get x transpose x whole inverse multiplied by x transpose x. And then we write beta as it is. Now, if we look at this term, we have inverse of a matrix multiplied with the same matrix. So we use the result that a matrix multiplied with its inverse gives the identity matrix. And we get identity matrix multiplied with beta. Next, we use the result that an identity matrix multiplied with any matrix gives the matrix back. And therefore, we have identity matrix multiplied with beta is equals to beta. So we just proved that the first term we have over here, which is x transpose x whole inverse x transpose x beta, is actually equals to beta. So we put this value back in the estimation error quantity and we get the first term is equals to beta. The second term we write as it is and the third term is minus beta. We can cancel out beta over here and we will be left with x transpose x whole inverse x transpose epsilon. And we have an estimation error of beta hat is equals to x transpose x whole inverse x transpose epsilon. But the goal is to prove that this estimate is unbiased. Let's look at the definition of unbiasedness. Say we have a parameter theta and its estimate is theta hat. We say that theta hat is unbiased if expectation of its estimation error is equals to 0. And therefore, we just need to prove that expectation of beta hat minus beta is equals to 0. We have just seen the value of an estimation error, which is x transpose x whole inverse x transpose epsilon. Perfect. So now if we look at the matrices inside the expectation sign, we have x transpose x whole inverse x transpose times epsilon. Now the matrix we have that involves the x matrix would be a fixed quantity. X is a deterministic vector. And since it is a deterministic vector, we can just pull it out of the expectation sign. And this is what we get. We have x transpose x whole inverse x transpose times expectation of error term. We have an assumption on multiple linear regression model that expectation of epsilon is equals to 0. We use that assumption over here and we have 0 times this x transpose x whole inverse times x transpose is equals to 0. And this gives us that beta hat, which is an estimator of beta obtained using ordinary least square estimation method, is unbiased. So now we have proved that this ordinary least square estimate of beta is unbiased. We can move forward and find the variance of this beta hat. Since we are dealing with matrices, we would find the covariance matrix of this beta hat. Variance of beta hat is equals to variance of x transpose x whole inverse x transpose y. We have just plug in the ordinary least square estimate of beta over here, and we have this value. Next, we use a formula of variance, that variance of a matrix A multiplied with x is equals to A times variance of x times A transpose. We use that formula over here and treat x transpose x whole inverse x transpose as a fixed matrix A. Applying that formula would give us x transpose x whole inverse x transpose times variance of y times the transpose of x transpose x whole inverse x transpose. To simplify it further, we write the first term as it is. But for the second term, we use the consequence of the assumption of error term on the dependent variable. And we have that variance of y is equals to sigma square identity matrix. And the third term, we write as it is. If we look at this quantity now, here we have this sigma square, and this sigma square is a scalar quantity. It is not a matrix. And since this sigma square is a scalar, we can just write it in front of all the matrices we have over here. And thus we have sigma square x transpose x whole inverse x transpose multiplied with identity matrix times the transpose of x transpose x whole inverse x transpose. Next, we use the result that the identity matrix multiplied with any matrix gives us back the matrix itself. And thus we have sigma square times x transpose x whole inverse x transpose times the transpose of x transpose x whole inverse x transpose. So now we have sigma square a scalar multiplied with x transpose x whole inverse, which we cannot simplify any further, multiplied with x transpose. But we have the transpose of x transpose x whole inverse times x transpose, and we can simplify the second term over here. So let's try to simplify the second term. We have x transpose x whole inverse x transpose whole transpose. Here we have the transpose of a matrix X transpose X whole inverse and X transpose. So we use a property of transpose over here, that is AB whole transpose is equals to B transpose A transpose, and using this property of transpose we have X transpose transpose multiplied with the transpose of X transpose X whole inverse. Next, we use another property of transpose, that A transpose transpose is equals to A. When we use this property of transpose, we have the first term, which is the transpose of X matrix, gives us X. And the second matrix, which is the transpose of X transpose X whole inverse, we write it as it is. Next, we write the matrix X as it is because we can't really simplify it any further. But we can simplify the second matrix. How? For that, we use a property of transpose, that is the transpose of an inverse of any matrix is equals to inverse of the transpose of that matrix. We use this property of transpose over here and we get this second term X transpose X whole inverse whole transpose is equals to, we can just interchange transpose and inverse and we have it equals to inverse of transpose of X transpose X. Further, we write the matrix X as it is. But if we look at the second term inside the inverse, we have transpose of the matrix X transpose X. And here we can apply a property of transpose, that X transpose X whole transpose is equals to X transpose X. And that gives us X transpose X whole transpose is equals to X transpose X. We use this result over here and we get that the transpose of X transpose X whole inverse, X transpose is equals to X times X transpose X whole inverse. And we have simplified the second term we have in the covariance matrix of beta hat. This is what we had. Variance of beta hat is equals to sigma square X transpose X whole inverse X transpose multiplied with the transpose of X transpose X whole inverse X transpose. We write the first term as it is, which is sigma square X transpose X whole inverse X transpose. And now the simplified version of the second term is just X times X transpose X whole inverse. Next, we write sigma square as it is. We write inverse of X transpose X as it is. And we group X transpose X together. We just multiply X transpose X first and write X transpose X whole inverse then. And if we look at this term now, we have inverse of a matrix multiplied with that matrix. When we multiply a matrix with its inverse, we get identity matrix. And therefore, we have sigma square times identity matrix times X transpose X whole inverse. We use the fact that identity matrix multiplied with any matrix gives us the matrix itself. And we have sigma square X transpose X whole inverse. And this is the covariance matrix of the vector beta hat, which is an ordinary least square estimate of beta.